In this program, we are going to talk about polarization in dielectrics, the dielectric constant, the linear, homogeneous and isotropic dielectric, boundary conditions, capacitance, some examples on capacitance, and finally the capacitance of a two-wire line. So, we start off with polarization in dielectrics. The main difference between a conductor and a dielectric lies in the availability of free electrons in the outermost shell to conduct current. Although the charges in a dielectric are not able to move about freely, they are bound by finite forces and experience a displacement when an external force is applied. To understand the effect of an electric field on a dielectric, consider an atom of the dielectric consisting of a negative charge minus q, which is the electron cloud, and a positive charge plus q, which is the nucleus. A similar picture can be developed for a dielectric molecule. We can treat the nuclei in the molecule as point charges and the electronic structure as a single cloud of negative charge. Since we have equal amount of positive and negative charge, the whole atom is electrically neutral. When an electric field is applied, the positive charge is displaced from its equilibrium position in the direction of E by the force F plus is equal to QE, while the negative charge is displaced in the opposite direction by the force F minus is equal to minus Q into E. In the figure 6.1, we can see in figure A that when no electric field is applied, the center of the positive charge and the negative charge coincide. But when an electric field is applied, it is equivalent to the case when E is equal to 0 plus a dipole is formed. That is, the negative charge and the positive charge no longer coincide, rather they are displaced by a distance d. And this is nothing but the formation of a dipole, where P is the dipole moment, which is equal to QD, where Q is the charge and D is the displacement between the negative charge and the positive charge. If there are n dipoles in a volume del V of the dielectric, the total dipole moment due to the electric field is given by equation 6.1b. As a measure of the intensity of the polarization, we define polarization P, that is the dipole moment per unit volume of the dielectric, given by equation 6.2, that is P is equal to limit del V tends to 0 summation of Qk dk from k is equal to 1 to n upon del V. The unit of P is coulomb per meter square. Thus, we conclude that the major effect of the electric field E on the dielectric is the creation of dipole moments that align themselves along the direction of the electric field. This type of dielectric is said to be non-polar. Example of such dielectrics are hydrogen, oxygen, nitrogen and the rare gases. Non-polar dielectric molecules do not possess dipoles until the application of an electric field. On the other hand, we have molecules such as water, sulfur dioxide and hydrochloric acid, which have inbuilt permanent dipoles that are randomly oriented and are said to be polar. When an electric field E is applied to a polar molecule, the permanent dipole experiences a torque that tends to align it along the direction of the electric field, as can be seen in figure 6.2. We shall now calculate the field due to a polarized dielectric. Consider in figure 6.3 a dielectric material which has dipole moment P per unit volume, and we are required to find out the potential at point O, whose coordinates are x, y and z, due to the dipole moment P dV dash, as can be seen in figure 6.3. The incremental potential is given by equation 6.3, given by P dot AR dV dash upon 4 pi epsilon naught r square. Now, it is readily shown that the gradient of 1 by r with respect to the primed coordinate is given by del prime 1 by r is equal to AR upon r square. Thus, P dot AR by r square is equal to P dot gradient of prime of 1 by r. Now, applying the vector identity shown at the top of the slide, we get equation 6.4, which is equal to P dot AR by R square is equal to divergence of P by R minus divergence of P by R. Substituting this value given in equation 6.4 into 6.3 and integrating over the entire volume V dash of the dielectric, we obtain the expression for potential. Now, applying divergence theorem to the first term of the above equation, we get two parts. One is a surface integral while the other is a volume integral, as given in equation 6.5a. Now, in the previous program, we had got the expression for potential due to a surface charge given by equation 6.5b and the potential due to a volume charge which is given by equation 6.5c. When we compare the two terms on the right hand side of equation 6.5a with that of 6.5b and 6.5c, we find that rho Ps is equal to P dot An while rho Pv is equal to minus del dot P. In other words, equation 6.5a reveals that when polarization occurs, an equivalent volume charge density rho Pv is formed throughout the dielectric, while an equivalent surface charge density rho Ps is formed over the surface of the dielectric. We refer to rho Ps as the bound surface charge density while rho Pv as the bound volume charge density, while rho s and rho v are the free surface charge density and volume charge density respectively. The total positive bound charge on surface S bounding the dielectric is given by equation 6.7a, which is equal to Qb, and the charge that remains inside the surface is given by equation 6.7b, which is equal to minus Qb. Now, since the dielectric was electrically neutral before polarization, therefore total charge will be equal to 0. We now consider the case in which the dielectric region contains free charge. If rho v is the free charge volume density, then the total volume charge density rho t is given by equation 6.8, and after some manipulations and simplification, we finally get the expression for d, the electric flux density, equal to epsilon naught into E plus P, where P is the polarization. This leads us to the conclusion that the net effect of the dielectric on the electric field E is to increase d inside it by an amount P. In other words, due to the application of electric field to the dielectric material, the flux density is greater than it would be in free space. It should be noted that the definition of d for free space is a special case of that of d is equal to epsilon naught into E plus P, because P would be 0 in that particular case. Now, for many dielectrics, P is proportional to the electric field applied, and we can expect equation 6.11, that is P is equal to susceptibility into epsilon naught into E. Next, we come to dielectric constant. Now, by substituting P is equal to susceptibility into permittivity E naught into E into d is equal to E naught E plus P, we get d is equal to epsilon naught into E, where absolute permittivity is equal to permittivity of free space into relative permittivity. Also, relative permittivity is equal to 1 plus susceptibility. Here, the permittivity of free space is approximately equal to 10 to the power of minus 9 upon 36 pi farad per meter, and ER is called the dielectric constant or relative permittivity. Here, the table shows that the relative permittivity of barium titanate is as high as 1200, while the value of relative permittivity of air at 1 atmosphere is only 1. Next, we come to linear, isotropic and homogeneous dielectrics. A material is said to be linear if d varies linearly with E, and nonlinear otherwise. A material for which permittivity does not vary in the region being considered and is same at all the points, then that material is said to be homogeneous. On the other hand, a dielectric material is said to be inhomogeneous when permittivity is dependent on the space coordinates. The materials for which D and E are in the same direction are said to be isotropic. That is, isotropic dielectrics are those which have the same properties in all directions. For anisotropic dielectrics, D, E and P are not parallel. In such cases, the permittivity or susceptibility has 9 components and together they are known as tensor. For most of the time, we are concerned only with linear, isotropic and homogeneous medium. For such media, all formulas derived for free space can be applied by merely replacing epsilon naught by epsilon naught into relative permittivity. For example, for the Coulomb's law, the force now becomes Q1 into Q2 upon 4 pi epsilon naught relative permittivity into R square into AR given by equation 6.17, and for energy it becomes equal to equation 6.18. Next we come to the boundary conditions. Till now we have considered the existence of the electric field in a homogeneous medium. If the field exists in a region consisting of 2 different media, then the conditions that must be satisfied at the interface separating the media are called the boundary conditions. These conditions are helpful in determining the field on one side of the boundary when the field on the other side is given. It also helps us in finding out the refractive index. The conditions will be governed by the type of material the medium are made of. We shall consider the boundary conditions at an interface separating number 1 dielectric and dielectric, second dielectric and conductor, and third conductor and free space. To determine the boundary conditions, we shall make use of 4 things. Firstly, we shall make use of the Maxwell's equation given by equation 6.19. Secondly, we shall be making use of Gauss's law given by equation 6.20, that is d dot ds over the closed surface is equal to q enclosed. The electric field E would be decomposed into 2 components Et and En, where Et and En are the tangential and normal components of the electric field intensity. Similarly, we will decompose D into 2 components D, T and Dn. We take the first case, which is the dielectric boundary condition. Here we have 2 different mediums having permittivity epsilon 1 and epsilon 2. We break E1 into 2 parts, E1t plus E1n, and similarly we break E2 into E2t plus E2n. Next we apply equation 6.19, that is Maxwell's equation, that is line integral E dot dl is equal to 0 to the closed path ABCDA, assuming that the path is very small with respect to the variation of E, and we get E dot dl is equal to E dot dl from A to B plus E dot dl from B to C plus E dot dl from C to D plus E dot dl from D to A, which is equal to 0. And when we put down the values as given in figure 6.4 and solving, we get equation 6.25, that is E1t is equal to E2t, which implies that the tangential component of E are the same on the 2 sides of the boundary, that is Et undergoes no change at the boundary and is said to be continuous across the boundary. Since D is equal to epsilon into E, which is equal to dt plus dn, equation 6.25 can be written as E1t is equal to E2t, which is equal to E1t by epsilon 1 is equal to D2t upon epsilon 2, and we get equation 6.26. It implies that the tangential component of D undergoes some change across the surface, that is dt is said to be discontinuous across the interface. Similarly, we apply the Gauss's law to the cylinder as can be seen in figure 6.5, and on applying that and simplifying, we get equation 6.27, that is d1n minus d2n is equal to rho s, and under the condition if rho s, which is the free charge density placed deliberately on the boundary, we get d1n is equal to d2n. Thus, the normal component of D is continuous across the interface, that is dn undergoes no change at the boundary. Again, since D is equal to epsilon E, equation 6.10 can be written as E1 into E1n equal to E2 into E2n, which can be written as given in equation 6.29, which shows that the normal component of electric field is discontinuous at the boundary. Now, the three equations given below, that is E1t is equal to E2t, d1n minus d2n is equal to rho s, and d1n is equal to d2n, are collectively referred to as the boundary conditions for the dielectric media. The boundary conditions are usually applied in determining the field on one side of the boundary when the field on the other side is given, and for determining the refraction of the electric field across the interface. Now, as can be seen in figure 6.6, we have d1 E1 in medium 1 and d2 E2 in medium 2. From equation 6.30a, E1 sin theta 1 is equal to E2 sin theta 2. Similarly, we can find out epsilon 1 E1 cos theta 1 is equal to epsilon 2 E2 cos theta 2, which is given by equation 6.31b. When we divide 6.31a by 6.31b, we get tan theta 1 by epsilon 1 is equal to tan theta 2 by epsilon 2, and knowing tan theta 1 and tan theta 2, which is equal to ER1 upon ER2. From this, we can find out the amount of refraction. Thus, in general, an interface between two dielectrics produces bending of the flux lines as a result of unequal polarization charges that accumulate on the sides of the surface. Next, we have the conductor dielectric interface. Now, in this case, the electric field intensity in the conductor is 0. Again, when we apply the Maxwell's equation, that is E dot dl equal to 0 to the closed path A, B, Q, C, dPA, and on solving, we get Et is equal to 0, given by equation 6.33. Again, applying the Gauss's law, D dot ds is equal to Qs to the Gaussian surface, which is a cylinder in this case, we get dn is equal to rho s. Equation 6.33, that is Et is equal to 0 and dn is equal to rho s, are collectively called the boundary conditions for conductor dielectric interface. An important application of the fact that the electric field intensity is equal to 0 inside a conductor is its use in electrostatic screening or shielding. In the figure shown, if conductor A is kept at 0 potential, is surrounding another conductor B, then B is said to be electrically screened by A from other electric systems such as C. Similarly, conductor C outside A is screened by A from B. Thus, conductor A acts like a screen or shield, and the electric condition inside and outside the screen are completely independent of each other. The third case is the conductor free space boundary condition, which is a special case of the second case. Here, the conditions which are seen in the second case, we simply replace ER by 1, that is dt is equal to E naught into Et is equal to 0, that is Et is equal to dt is equal to 0, and dn is equal to E naught into En, which is equal to rho s. The above two equations imply that E field must approach a conduction surface normally. Next, we come to the capacitance. A capacitor must have two conductors carrying equal but opposite charges. This implies that all the flux lines leaving one conductor must necessarily terminate at the surface of the other conductor. The conductors are referred to as the plates of the capacitor, and the plates are separated by a free space or a dielectric. Now, when we consider a two conductor capacitor which are maintained at a potential of V given by V is equal to V1 minus V2 is equal to integral of E dot dl from 2 to 1, then the capacitance can be equated to Q by C, which is given by d dot ds over the closed surface upon line integral E dot dl. The negative sign before V is equal to minus E dot dl has been dropped deliberately because we are interested only in the absolute value of V. The capacitance C can be obtained for any given two conductor capacitance by following either of the two methods given below. First, assuming Q and determining V in terms of Q, that is involving Gauss's law, and second, assuming V and determining V in terms of Q involving solving the Laplace's equation. Here we shall talk about the former method. The modus operandi for the first method is choose a suitable coordinate system, let the two conducting plates carry charges plus Q and minus Q, determine E using the Gauss's or Coulomb's law, and from that find out V from the equation V is equal to minus integration of E dot dl. Finally, C can be obtained using the equation C is equal to Q by V. We now apply this procedure for some different two conductor configurations. First, we have a parallel plate capacitor where the positive charge is on the top conductor and negative charge is on the bottom conductor, which are separated by distance d, and the surface charge density is given by Q by S. If the space between the plates is filled with a homogeneous dielectric with permittivity epsilon and ignoring the fringes at the edges of the plates, from the expression derived for capacitor in third program, that is E is equal to rho s by epsilon naught into A n, for the region between the two plates of a capacitor, we get D is equal to minus rho s into A x, which can be further modified as equation 6.38, and using that value of E, we can find out the value of V, which is equal to minus integral of E dot dl from 2 to 1, which finally gives us Q d by epsilon into S, that is C is equal to Q by V equal to epsilon S by D. This formula, it offers a means of finding the dielectric constant epsilon r of a given dielectric. By measuring the capacitance C of a parallel plate capacitor with the space between the plates filled with the dielectric and the capacitance C naught with air between the plates, we find epsilon r, that is relative permittivity, from epsilon r equal to C by C naught. Similarly, we can find out the energy stored in the capacitor given by equation 6.42. The second is the coaxial capacitor, which is essentially two coaxial conductors of inner radius A and outer radius B, where B is greater than A. The inner cylinder carries charge plus Q, while the outer cylinder carries charge minus Q. By applying Gauss's law to an arbitrarily Gaussian cylindrical surface of radius rho, which is between A and B, we obtain equation 6.43, and from that we can find out the electric field intensity, which is equal to Q upon 2 pi epsilon rho L into A rho. Neglecting the flux fringing at the cylindrical ends, we can get the expression for V, which is equal to minus E dot dl from integral from ranging from 2 to 1, and we get the expression for V given by equation 6.45b, which is Q upon 2 pi epsilon into L logarithm of B by A. This way, putting the value of V in the expression 6.46, we get the expression of C is equal to Q by V, which is equal to 2 pi epsilon L upon logarithm of B by A. We can follow the similar process for the spherical capacitor, where we have two spheres, the inner sphere having radius A and the outer sphere of radius B carrying charges plus Q and minus Q respectively. By applying Gauss's law to an arbitrarily Gaussian spherical surface of radius r ranging between A and B, we can get the expression for Q given by equation 6.47. And from that we can find out the value of electric field intensity. Further, we find out the value of V given by equation 6.49. Having done that, we find the expression for C, which is equal to Q by V, which comes out to be 4 pi epsilon upon 1 by A minus 1 by B. Finally, we come to the capacitance of a two-wire line. The two-wire line configuration consists of two parallel conducting cylinders, each of circular cross-section. We are required to find the complete information about the electric field intensity, the potential field, the surface charge density distribution, and the capacitance. In the figure 5.16, we have two parallel infinite line charges carrying opposite charges. The positive line is at x is equal to a, y is equal to 0, while the negative line is at x is equal to minus a, while y is equal to 0. The field point is at P in the xy plane is radially distant r1 and r2 from the positive and negative lines respectively. The equipotential surface are circular cylinders. We get a general value of potential given by equation 6.51, which is V is equal to rho L upon 2 pi epsilon into logarithm of r naught by r. This formula is then extended for the combined potential field in terms of the radial distance from the positive and negative lines r1 and r2 respectively, given by equation 6.52. We choose r10 is equal to r20, thus placing the 0 reference at equal distance from each line. This surface is the x is equal to 0 plane, that is yz plane. Expressing r1 and r2 in terms of x and y, we get the equation 6.53, where we have everything in terms of x and y. In order to recognize the equipotential surfaces and adequately understand the problem we are going to solve, some algebraic manipulations are required. We choose an equipotential surface V is equal to V1 and define K1 as a dimensionless parameter, which is a function of potential V1. We get the expression for K1 given by equation 6.54. So that K1 is equal to x plus a square plus y square upon x minus a square plus y square. After multiplying and collecting like powers, we obtain the first equation given at the top of the slide. We next complete the square given in the second equation of the slide, showing that V is equal to V1 equipotential surface is independent of Z and intersects the xy plane in the circle of radius B, where B and H are shown in the slide. We solve the last two equations for A and K1 in terms of the dimensions B and H, whereby we get the expressions for A and K1 given by equations 6.55 and 6.56. But the potential of the cylinder is V naught, so equation 6.54, it leads us to the value of K1, and therefore rho L is given by 6.57, that is rho L is equal to 4 pi epsilon V naught upon log of K1. Thus, given H, B and V naught, we may now determine A, rho L and the parameter K1. The capacitance between the cylinder and plane is now available. For a length L in the Z direction, we have C is equal to rho L upon V naught, which finally is equal to 2 pi epsilon L upon cos hyperbolic H by B. Now, summarizing this program, we initially talked about polarization in dielectrics, where we introduced a new vector polarization, that is dipole moment per unit volume. Thereafter, we discussed dielectric constant, which was followed by linear, homogeneous and isotropic dielectrics. This was followed by boundary conditions, where we took the following three cases: dielectric dielectric, dielectric conductor and conductor free space. This was followed by a discussion on capacitance, we talked about some examples, and finally we talked about the capacitance of a two-wire line. Thank you. I hope you enjoyed this program.